hit the record button and begin. Heavenly Father, we thank you for this day again. I thank you for this class, this time we have to meet and study your creations. Pray we'd all understand a little bit more about classical homology today, Lord. You know my prayer, Lord Jesus. Amen. All right, so let me get started here. So our goal in this week is to describe a method of calculation that will let us sort of capture whether or not a space has hole in it. And it's kind of a mixture of classical geometric stuff and linear algebra. And so we'll start with, and I'm following Rentland, chapter 5, which he has entitled Elementary Homology Theory. So this is his, let's see here, Manifolds, Tensors, and Forms, Introduction for Mathematicians and Physicists. And so he starts, well, there's a great quote at the start of this. It says, in these days, the angel of topology and the devil of abstract algebra fight for the soul of each individual mathematical domain. It's a quote from Herman Weil. Okay, so getting to the point here. I think we've already defined convex, so you guys know what that is. The convex hull of a set is the smallest convex set containing U, all right? So the convex hull of U, subset of Rn, let's say, is smallest convex set containing U. All right. Convex definition. U, well, let's say not U, let's say S. That's fine. S, a subset of Rn, is convex if given X and Y in S, the line segment X comma Y is a subset of S. Right, and here I'm using the notation, X comma Y is what? Let's see here, Tx plus 1, oh man, that's not it. X plus, no, I'll get it eventually here. X plus T times Y minus X, such that 0 less than or equal to T less than or equal to 1. That's the usual parameterization that, takes you from X to Y, right? Okay. So, all right. So he says the convex hull of U, you can define the convex, and his notation, I guess, I don't know if this really matters too much, but conv U is equal to the intersection over all convex V such that U is a subset of V, right? You could define the span in a similar fashion in linear algebra. I don't usually do that, but if you wanted to, you could, right? Like the span of a set of vectors, it's the intersection of all possible subspaces which contain said vectors, right? Which means that the span of a set inside a vector space is actually the smallest subspace which contains S, right? You could define span in that fashion. The convex hull is defined in that same way. All right, so So if just for an example, if I was to, say that these 3 points, right? If I was going to say, my U was these 3 points, what would the convex hull be? The triangle. Yeah, so the triangle, right? And all the points inside it, right? So that would be the convex hull of that. So it's like that, yeah. All right. Move on here. Let V be an element of Rn and A in R, G the usual Euclidean metric, any set of the form. Okay, so here's the next definition. If we have X in Rn such that G of X comma V equals to A, this is a fine hyperplane. Now, in our usual notation, we would just write this like X dot V equals to A. All right. So like example 2, we could have, XYZ dot ABC equals to, D, for instance. Hopefully you recognize that from Calc 3, right? Yeah. I like that you laugh.
Actually, it's funny because
Uh-huh.
there's more to it, but I know that I don't remember actually.
Uh-oh.
Why is that? That's to do with like a normal something. Well, she just
Okay, so example 3, I could look at X comma Y in R2 such that, X comma Y dot A comma B equals to a constant, So that would define some particular line, right? So this is some line, right? But it could be a line. This is an actual plane in higher dimensions. It could be more. Okay. Anyway, the point is that it determines 2 closed half spaces. All right. So the 2 closed half spaces would be like the 2 closed half spaces. And those 2 closed half spaces, I'll do it up here in the general case. The 2 closed half spaces, what are they? You could have the one with G of X comma V greater than or equal to A, or you could have G of X comma V less than or equal to A. Like, let me make this a little bit easier. Let's just make this, 1, 1. Right? And 1. So this is what? This is just X plus Y equals to 1, so Y is 1 minus X, With those choices, I can take the ambiguity out of all this. This is L, right? So it's fairly clear what the defining half spaces are, right? Up here, we'd have X plus Y greater than or equal to 1, right? And then down here, we'd have X plus Y less than or equal to 1, I think. Yes, no, maybe so. So these are the two half spaces. Okay? But we can just as well do that in 3 dimensions. You're either on one side of the plane or the other. We're defining all of 3-dimensional space into two so-called closed half spaces. All right? He says, the affine hyperplane H is a supporting hyperplane. Come on. The affine hyperplane H is a supporting hyperplane of an n-dimensional polytope P if H meets P in some non-empty in some non-empty set. And P is contained in one of H's closed half spaces. All right. He says any set, if you have F, is formed by the intersection of the polytope with the half space. All right. It's called a face of P. All right. So some examples of polytopes are given in like figure 5.3. So some pictures we should thinking about for polytopes are like, you know, a triangle, all right, a square, maybe a tetrahedron, a cube. These are all examples of polytopes, all right? He says the definition allows for F equals to P. All other faces are proper. Right. So if F is not equal to P, then F is proper face of the polytope. All right. The dimension of the face, what do you think we should define that to be? Probably n. I don't think so. So here's the deal. The dimension of the face is the dimension of smallest affine space containing F. So like, if you think about the triangle, all right, is the polytope, all right, and you think about it, I mean, so I'm talking, let's talk about the shaded in triangle too, all right, so this thing, right? If you think about the whole triangle would intersect with the plane of the board, right? And the smallest affine subspace which contains the entire triangle is two-dimensional, so I make it a two-dimensional face. It's not proper because it's the whole triangle, right? On the other hand, if I look at, you know, yeah, I can, for example, take this, you know, as my, you know, affine hyperplane, then that would make this right here be a face, right? It's contained in a one-dimensional affine hyperplane, namely a line, and that makes that face one-dimensional. So the line segment's one-dimensional, right? It is a face because the whole triangle's in the upper half plane, right? Like I can't do, for example, this, right? We're forcing it to cut on the edge. Yeah.
Can we cut the vertex, but not alongside?
Yeah, I think so.
You know what I mean? We have a zero-dimensional face.
Right, exactly. So, indeed, if you just did like this, that would show you that the vertex is also an example of a face. Not that I just labeled it zero. It's a zero-dimensional face, right? Because that intersects with the point, which is just the vertex, which is a zero-dimensional affine space. What's an affine space? An affine space. So if you got a vector space V, and if you have W as a subspace of V, then P plus W is an affine subspace. It's just basically a parallel translate of a subspace of the vector space. Now, although we're not really doing vector spaces here so much as we're just doing things in Rn, okay? But all right, let me go on here. So a zero-dimensional face is called a vertex. So this is a vertex. Come on. So here's some terminology: zero-dimensional face, one-dimensional face, vertex, edge. What do you call right, n minus one dimensional. What is it?
Oh, nothing.
Two-dimensional face is just a face? Yeah, no. Uh-oh, I don't want to know. All right, so n-dimensional face is called a facet. So that depends on, basically codimension, right? So like a plane in 3 dimensions is a facet. Well, a two-dimensional, what I would actually call a face in a 3-dimensional polytope, right? Like a face of the cube is a facet if it's a cube in 3 dimensions, you know? All right, great. Let's try to make sure I don't miss anything here. The collection of all facets, what's that called? The collection of all facets of polytope is what? We'll say this.
But does the facet contain, facet would contain the edges?
Right, yeah, the facet contains the edges and it contains the vertices. So as a point set, it's the boundary. What's the interior of the polytope? We could just take the polytope and remove the boundary, right? So there's the interior. All right. He says, because polytopes have many facets or seats, they're also called polyhedra, meaning many seats. He says, it seems obvious that a polytope is the convex hull of its vertices, and that every face is the convex hull of some subset of vertices, but the proofs are surprisingly subtle, so we'll omit them. He gives a reference. We will also be omitting them. All right, but it is pretty obvious from all of our examples that to get any face of the cube, you would take the convex hull of the vertices of that face, right? And every facet of one of these is the convex hull of some subset of all of them. And if you take the convex hull of all of the vertices, it's pretty clear that it gives you back the polytope. You know, I think that it's geometrically clear that that's true. All right, so next up, let us move on. So, I have to land the plane this week, right? I don't have another. We're at a runway at the end of this week, I think, pretty much. You know. So I must forge ahead. Also, there's really nothing more to say about what we've been doing so far, so it is time to go ahead. Let's do that. So these definitions will probably be new. Definition: a set of points P0, P1, P sub D. So that's a subset of Rn here, okay? Is a finely independent. Finally independent. If the vectors P1 minus P naught, P2 minus P naught, P3 minus P naught, all the way out to P sub D minus P naught are what? Linearly independent. All right. A simplex what's a simplex? A simplex is the convex hull of an independent set of points. And we're going to put some parentheses around this because we don't want to keep saying it finally 1,000 times here, because it's clear we're talking about a fine independence. If we're talking about independence of points, you know, although I guess it's not entirely clear because every point is a vector from the origin. So you can talk about the independence of points as vectors from the origin as well. But let it be understood I'm talking about, you know, let me just use abbreviation. How about that? Simplex is a convex hull of an finally independent set of points. And we have notation. So if S is a finally independent, then this bracket S is going to be the convex hull. Is the simplex determined given by. So this is notation for conv. He's introducing now notation. Instead of writing conv S, he's writing brackets S. All right. If the cardinality of the set S is equal to D plus 1, then the dimension of the simplex is D. All right. And in this context, we'd call this a D simplex. So some examples. What example am I on? 3, maybe? You know, if my S is 1, 2, 3, 4, right? So 1, 2, something like that, right? There's my S. So there is the simplex, right? This is a 1 simplex because it's generated by 2 points. It's a one-dimensional simplex. If I had right, then the simplex is and all these points as well, right? The convex hull of these 3 points. So this T is a 2 simplex, right? It's generated from 3 independent points. What would it mean for the points not to be independent? What would they say about them? If I had 3 points which were not finally independent, what would that mean about them? Yeah, they'd be collinear. Yeah. Or worse yet, they're just the same point. Right? But I don't know. I guess that begs the question: how can you have 3 points? Well, anyway, let's not. Let me shut up. No one cares. So no one cares. So where was I? Triangle is a 2 simplex. A tetrahedron is a 3 simplex. All right. The vertices of the simplex generated by S are simply the points of S, and because a subset of an independent set of points is itself independent, any proper subset. This is a theorem. Lemma. If S is affinely independent and T is a subset of S, then T is affinely independent. I totally should have made that a homework problem. Oh well, too bad I didn't write your homework. Where else can I put things? Oh yeah.
This is probably really easy for to get into.
Haha.
Probably 3 lines.
So if I put it on the test, you guys are all going to get it. That's what you're telling me.
Are you looking in the textbook and seeing that it's not?
No, it just says it. It doesn't. This is not the kind of thing this book's going to prove. This book only proves non-trivial things. Like it's not, Okay, so what that means then is any subset of our set of vertices will then, so in the same way you're going to have the simplex determined by T is going to be a subset of the simplex determined by S, right? So like maybe we're talking about, the tetrahedron where we have, these 4 points. And these 3 points are a proper subset of that. And of course, they're going to generate just that face. Whereas if you take the whole simplex, it's got everything, inside as well, So here I'm thinking of P1, P2, P3, P4, and I'm saying that the face is P1, P2, P3, and that's a subset of the, the one that's, and you know what, well, fine, I really don't like writing the curly brackets here, but I gotta be careful. There is a very particular notation we're about to introduce, so let me just, there it is, all right. Okay, so, so this, if this is the situation up here, if, the dimension of T is equal to K, then this is a K face of the simplex that's generated by S, right? It's a K face. The 0 faces are vertices, the 1 faces are edges, the n-1 faces are facets. All right, great. Let's see here. He says, as we've defined them, geometric simplices are closed subsets of Rn. Given an independent set of points, P0 through Pn, one can also define an open simplex as follows. Like an open simplex, well, it's not just that. Oh, okay. So like open, let me just make a remark here. That's kind of interesting. If you had S, P0, P1, Pn, so that's got n+1 points in it, right? Then if you look at the sum I equals 0 to n of T sub I, P sub I, where T sub I greater than 0, and also T0 plus T1 plus plus Tn is less than 1. That gives you the open simplex. So this, all such points are, this is what's meant by that, like this parentheses, the open simplex determined by the affinely independent points S. And likewise, you could define open faces, right? You could define open faces in the same way, right? So the open faces are going to like be missing vertices and edges if it's a two-face, an open two-face, right? Open one faces are going to be missing their vertices, you know. He says this is actually also the topological interior of the closed simplex. I mean, the simplex, in the way we've defined them, they're all closed, right? Line segments are closed. All of these simplices, they're closed. All right, great. So far so good, I think. So now we come to the main definition, as he says. A simplicial complex what is this? K is a finite collection of simplices satisfying two properties. Number one, if S is in the simplicial complex and T is a subset of S, all right, then the simplex generated by T is also in the complex, all right. In words, that says every face of a simplex in K is a simplex in K, right? So this would make T a face of the simplex S, right? So it's saying if you have a simplex in the complex, all of the subfaces of the simplex must also be in the complex. So if you had a tetrahedron in the complex, all of its all of its two faces, all of its edges, and all of its vertices are also in the complex, for instance. And then two, if for any, say S1 and S2 simplices in the complex, comma, continue the sentence down here, the intersection of these simplices is equal to the simplex generated by the intersection. Right. What this says is if two simplices meet, they do so along a mutual face. All right. All right. The dimension of K is the max dimension of any of the faces it contains, I guess. Well, I should say not faces, simplices. Sorry, simplices. All right. So he says intuitively, a simplicial complex is simply a set comprising a bunch of simplices that are glued together along their faces. All right. Let's see here. Let's see if we can, before we go on to the next definition, which is, actually where it starts to really get interesting. To my taste, everything up to this point is just kind of setup. It starts to really get interesting with the next definition. But before we get there, can you guys tell me, like, how would this not happen?
If we have two cubes that
Oh, okay.
are too close, like they could go through each other. Or two squares that go through each other.
That maybe, yeah, two square. I like two squares better. That's better. So,
Two pieces of paper that are lined up on each other.
so if I had two squares like this,
Or if you had something like that, rectangle, you drew over there. If you want that change.
oh, oops. So this one here, yeah, so if I take S1 to be this, right? And I take S2 to be the set of these 2 points, right? Then this right here is the simplex generated by that, right? And this edge right here is the simplex generated by those 2 points, right? And where do they meet? Well, they do intersect, right? So the intersection of these 2 things is this point right here, right? But that point is not, that's not in the simplex I'm considering. So let's just say that point's not there. If that point's not there, then I don't have, I don't have this in there. I guess if I threw the point in, though, maybe this would still be okay. Yeah. Like if I have the 2 squares, but I also include the points of intersection to fix this. If this point's missing, I'm in trouble.
But wouldn't that not be linearly independent?
Not be linearly independent. Well, there's no assumption that the there's the
If we just throw the point in there, it's like a little one.
well, see, the simplicial complex is a collection of simplices, so I can just throw points in as zero faces if I wanted to.
Wouldn't that not be a simplex anymore? Unless it was like a different simplex.
I mean, this might still not be a simplex because of other reasons. There's a lot to check, in terms of like, for it to be a simplex, I have to like include, I have to include the whole, like the 2 faces, like the shaded in square, the shaded in square, all of the edges of both, and then all possible. So I don't know. I mean, I don't know. I'm not sure that can be. I'm not sure it can be repaired by just adding the point. There may be more to it. I'll save that for your test. So let's go on here. The thing is, we don't have to make ugly. Complex, we don't have to make an ugly complex. We can make complex. The complex is nice and simple as we need to calculate the topological objects we're looking at. So there's no, we don't have to consider all possible. So here's where the logic goes. We don't have to consider all possible, triangulations. Ultimately, this gives you like a triangularization of the space. It's enough to find one triangularization of the space and calculate things from that. So like the fact that there's another one that's more ugly, it doesn't much matter because there's like theorems that say that the things we calculate from these triangularizations are independent of our choice of triangularization, which is pretty fascinating. Anyway, so let's move on here. So oriented simplices is our next move. So it's useful to assign an orientation to a simplicial complex. Oriented, so definition, oriented simplex. We'll use sigma bar for this, and we'll use the brackets to indicate that they're oriented. P0, P1, all the way out here to P sub n is a simplex and so notice I'm dropping the curly brackets also. I could have done it earlier. I mean, to be fussy, it's the set containing these points that you're generating the convex hull of, but I mean, this is not a large abuse, right? I'm not writing curly brackets. It's kind of like sometimes you're like inverse image of 1 when the function's not invertible. we're really saying inverse image of the singleton set, curly brackets 1, you know, and that's okay. Because who wants to write so many curly brackets? Well, me probably, but I try to resist my more base, you know, instincts. So, so this is, it's a simplex such that what? In which we have chosen an order for the points up to an even permutation. All right, so he says that all the simplices are divided into precisely 2 equivalence classes or orientations, depending on whether one chooses an odd or an even permutation of the vertices P0 through B1, Pn. So, with a chosen ordering of the points, right? So, all right, so here's, for instance, minus sigma bar would be something like P1, P0. Everything else the same, you know. On the other hand, sigma bar, again, you could do P2, P0, P1, Pn, because all I did here was I moved 2 transpositions over, right? So that's the, you know, we do sigma bar is one orientation for the simplex, and the opposite orientation we denote by minus, right? So let's see here, some examples. All right, so example, where was I? Example 6. If we had sigma bar is like P0, P1, you know, it would be like here's P0, here's P1, and we think of it not just as the line segment anymore, but now it's a directed line segment. It goes from P0 to P1. Right? On the other hand, if I wanted to think the other way, right, that would be what? Minus sigma bar, which would be P1, P0. Because it goes the other way. And if I add these, if I could do that, what would happen? I guess I wouldn't go anywhere, right? Sigma plus minus is 0. I'm not sure that's actually something we're going to do, but I can't remember. It's been a minute since I've covered this, you know. So I'm relearning this with you guys, which is what I like about this, because I forget it. You know, I've taught it a couple times before, but it fades. Example 7. What if we had 3? So P0, P1, P2. You know what? I'm going to do 1, 2, 3, if that's okay. 1, 2, 3. I do better with 1, 2, 3. Right? So if I do sigma bar is the set gendered by 1, 2, then 3. That's a two-face, right? It's an oriented two-face. In fact, an oriented two-simplex. So the right-hand rule kind of helps us out here. So the way that goes, you go 1 to 2, and then 2 to 3, and then 3 back to 1 again. So this is actually also equal to P, for instance, 3, P1, P2. It's also equal to P2, then P3, then P1. These are all the same. In contrast, we have minus sigma bar would be like P3, P2, P1, right? Which I'll draw a picture of over here so my picture doesn't get too busy. So minus sigma bar, it goes from 3 to 1. Wait a minute, what have I done? No, from 3 to 2. I can't read my own, dummy. Me, not you. 3 to 2, 2 to 1, 1 to 3, right? And so you could also write this P2, P1, P3, or you could write it as P1, P3, P2. There you go. Those are all 6 possible orderings of 3 points, right? 3 factorial 6. There's 6 arrangements to look at here, and they're divided into positive, and by our definition, the positive ones, by our definition, the negative ones. That's just an ad hoc choice, right? I could just as well have labeled this one the sigma bar, and then all of these would be the minus sigma bar. But traditionally, let's see here. Have I followed the right-hand rule, right? Oh, look, I chose poorly. This one is what? It's counterclockwise, so I chose poorly, right? I should have, it's not too late, is it?
Just erase.
It's not too late. Check it out, I'll fix it. Watch. Behold, behold. It is not too late.
It's too late.
It's not too late to...
I ordered you.
There you go. So you see the ordering of this oriented simplex business gives us a way of orienting faces algebraically. This is pretty neat. So we can also define, for like a tetrahedron, right? So if I do this as like P1, P2, P3, P4, if I wanted to give these faces it's like suppose I want to describe this face here, this one right here, with a outward orientation, like this kind of orientation. I want it to go like this, and then like this, and then like that. So I should describe that face as what? Start with P1, go to P2, P1 to P2 to P4. There you go. This one over here would be, let's see here, if I go, I'll start at P2, and then to P3, then to P4, then back again, right? So that would be like P2, P3, P4. All right, I think we got our bearings here, I think, about this notation, right? So what is an oriented simplicial complex? What do you think? Let K be an oriented simplicial complex. What does this mean? That is a simplicial complex where each simplice is assigned an orientation, right? So it is what it sounds like, right? An M chain on K with coefficients in R. Now this is where all of a sudden it gets a little bit, yeah.
Didn't I just reach simplex?
Oh. Thank you. Hmm? I mean, his grammar is slightly different and probably better than mine. Anyway, an M chain on K with coefficients in R is a formal linear combination of the oriented M simplices in K with coefficients in R. So C bar, typical M chain, sum over I of A sub I sigma bar sub I. Here, A sub I is in the reals. He says, subject to the convention that if sigma bar and sigma j, bar j, represent oppositely oriented simplices, then, well, in other words, we're going to keep using the sign convention I've already introduced, okay? So in this context, the thing I was kind of musing about actually happens. If we take sigma plus minus sigma, that would be an example of the formal linear combinations we're talking about. It would be 0, right? The vector space, this is an element of CM K. So let me try to, this will become more clear what we mean by formal linear combination as we work examples and things, but think of it this way. If, let's see here, suppose we're talking about 0 simplices, right? For the sake of discussion, you know? Which is like essentially the vertices which appear in the simplex, the oriented simplex, right? Then if you had, you know, say 8 of them, then the dimension of CMK is probably 8, you know? Assuming, of course, that the, well, that's the thing, is we do assume that the vertices, like, okay, so like, formal linear combination. So like this typical, like a typical point in here would be something like, you know, A1, goodness gracious, sigma 1. I kind of want to write P, but I'm going to do it. Typical point here would be something like A plus P1, A2 P2 plus da 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 plus A8 P8. Like that's a typical element of C0 K in this context. And in this context, you're going to completely ignore any kind of